So basically, this is what we have. This is the name of our experiment. Experiment 2, spectral composition of a black body radiation. So we want to compute some tables based on this particular thing. This thing called spectral flux density of a black body as a fraction of how much of this black body power you'll be able to access, and out of all that much which is available. So basically, this is a function for the spectral flux density. So we're going to do that, and we need a function for this. We had something which we created from the other lab, so we are going to rename our function, I think. So we're going to say create spectral flux density function, spectral flux density function. Based on this, we have a bit of experience with this particular function and how it works. So we're going to change the name to spectral flux density. So what does the function do? Computes the spectral flux density of a black body at temperature T using Planck. The Planck function. So here we have these variables. We need the A value. We also need the B for this particular thing here. So that's what we have here, A being equals to this. So our A is 3. So here next, create variables A and B. So that's your A in watts meter squared. And B in
Sam,
yes.
I wanted to ask, like in our work, are we also supposed to be writing like the title here to create spectral flux density, or we can just go straight?
You should do that. You can just type. You don't. It doesn't have to look like this. Just say create spectral flux density function. That's all. Otherwise, how else do you want to do it? You just want to do things without explaining what you're doing?
Yeah.
No. Okay. So next, you have to explain what you're doing. Import numpy by module using alias np. That's what you have here. We import numpy as np. So now, from our experience, there's something we noticed with this spectral flux density thing. You put in a temperature, then what we noticed is that for temperatures which were above 1000, we needed to come up with a different range. Okay, then for temperatures which were below 1000, we also needed to come up with a different range of temperatures. So basically, in our case here, if the temperature is above 1000, we're going to use the range, we're going to go up to 4000, or we're just going to go up to 5 micrometers. So in this particular case, we check if temperature is greater than 1000 kelvins. So in this case, if temperature is greater than 1000 kelvins, the temperature which you've entered here, if temp is greater than 1000 kelvins, then we want to produce a wavelength range starting from, if you look at your caves, 100 micron, starting from 100, or we can say 50, 100 or 50, 50, all the way up to 5000, and you want 5,000 points. So we want to generate a list of wavelengths in this particular range. So this is basically 50 micrometers all the way up to this. Is it microwatt? What do I have here? 8 to the power 9 nano and 5000. Yeah, so basically I think it should be the same up to this bit here. So basically here we say generate wavelengths in range of 50 nanometers to 5000. 50 nanometers to 5000 nanometers is the same as what we have here, which is what is, which is 5 micrometers, I think. Is that clear? 5 times 10 to the power minus 6. 5 times 10 to the power minus 6. That's 5 to the power 6. Then what I have here is 5000. 5000 times 10 times 10 to the power minus 6. No, to the power minus 9. 5000 times 10 to the power minus 9. It's the same. So in your graph is showing on the thing I've sent in your WhatsApp, on your WhatsApp group. That graph is showing showing things in terms of micrometers. We could still do that. In that case, it will have to be I'll have to, if I write 5 micrometers, it will be this. But this side, it will have to reduce of my 50. I'll need to divide it by 1000. So I'll end up with 50 divided by 1000. So I'll end up with 0.05. I'll end up with this. Which is the same thing. Are we clear? So I just stick to the nanometers. It looks better. So we're talking about the same thing here. So 50 nanometers is the same as 0.05 micrometers, and 5,000 nanometers is the same as what you have in your graph there, which is your 5 micrometers. Is it clear?
Yes, sir.
So if we say 0.05, if we want to do this 0.5 micrometers, then here it will have to go to 5 micrometers. So if you do that, if that's what you want to do, if you want to follow the what's on the graphs which we have there, because we have to produce those graphs, so that if we are able to produce these graphs, then we are sure that our function which you have written is working the way it's supposed to work. Are we clear? So -6. -6. Then we need 5,000 points. Then else, if the range is, if temperature is less than that, then we want to go from so here, yeah. So we want to generate, if the temperature is less than 1,000, so if the temperature is above 1,000, we want to use a wavelength which is only up to 5 micrometers. On the other hand, if the temperature is above 1,000, we want to generate a wavelength from 5 micrometers, from 0.05 micrometers all the way up to up to 100, all the way up to 100 micrometers. That's what we want to do. I hope it works. Okay, then after that, there is another term this bit here where you're multiplying wavelength times temperature. This, so that's what we work out. Calculate wavelength, calculate product wavelength times temp. So these, you multiply the wavelength times temp. That's what we're going to store as wave temp or wavelength temperature. We can call it wave temp, I think. This wavelength, just the, whichever we have it here, wavelength temperature here. So with that, set numerator and denominator. So here in our expression, there's a top part, which is this, which is the A. There's a bottom part, which is this bit here. So we're going to set those. Then after that, you're going to divide. So a numerator in this case is just going to be the A, set numerator A, then we set the denominator. So the denominator in this case is your wavelength raised to the power 5. Yeah. We use the power function, NP power, wavelength raised to the power 5 times this exponent raised to b minus this, then minus 1, like that. So when you do that, so this here, the first part, that's a wavelength here, wavelength raised to the power 5. So using n power, this is a numpy function, then times the exponent one, np dot exponent b divided by wavelength temperature. Then this other side, what do you have? Wavelength temperature, then minus 1. Yeah, there, minus 1. So that should give us a denominator. Then after that, we can work out our spectral return. So we can say we work out our spectral emissive power. So calculate spectral emissive power from numerator and denominator. That. So in that case, we're going to have that bit. Then after that, whatever we have there, want to retain return wavelength and spectral emissive power. So that's what we do. So basically this is what our function is supposed to do. This bit. Okay, so with that bit in mind, it's time for us to find out if this thing is actually if it works. Okay, so we have a temperature of 2000, then also we've got a wavelength of 2000. So the next thing we're going to do is we're going to import matplotlib. Matplot lib.yplot as POT, because we need to produce a graph. Remember, all these things I'm doing, when you do your thing, you don't have to show them. Just focus on what you need, because you don't have to produce a graph yourself. But we are testing this thing to show that if it works or not. Where we are here, on myself, I believe in your ability to repeat these steps. You will learn by repeating. When you do, whether you have to go and rewatch the video so that you do your stuff, you do that, you repeat, and that's how you're going to learn. Are we clear?
Yes, sir.
Yeah. So you select what you need, then you get the code you need, you put this whole thing together so that it does what we want it to do. Okay. So in this case, we're going to say import matplot matplotlib dot pyplot as PRT. Okay. All right. So the next thing we're going to do, we need things which are similar to that. We're going to call these functions. What do we do? Okay. We use these bits. We're going to make calls. So we're going to say wavelength, but in this case, our wavelength we're going to use is 2000. Wavelength 2000 kelvins. So wavelength for a temperature of 2000 and spectral flux density, spectral power for 2000. So we're going to say equals to spectral flux density at a temperature temp being equals to 2000. When you run that, then you can print out, see what you have for these guys. If things have worked, I'll print out. That bit, so that list has been generated. There are a lot of them, so you don't see, so that's why there is this bit here. Okay. For the spectral bit, I'll print out also. Spectral power. There. With these, we can have a good idea. We can make a quick plot. See if our things are working. So create a black body curve. Create a simple line plot, create a simple line plot, and import for black body curve, black body at temperature T equals to 2000. So we're going to say POT dot figure POT dot plot wavelength 2000 spectral stuff at that bit. Then we say POT dot show. You do that, that's what we get. So that is a cave at 2000. So the function seems to work. Seems to do. You see that this seems to match what you have in your what is in the lab thing I've sent you. Are we clear? Is it clear?
Yes, sir, it's clear.
Yeah. So it matches. So the thing works. It can produce the caves which we need. And this is the same function which we need for the other things which we have to do. So we'll do the same for the other temperatures. So copy. So we have 1700, 1750 kelvins, 1750 kelvins, and temperature this side 1750. Okay, then we have for 1500, okay. Then the last bit we have is the data for 1200, 1250, there. So we can make our plots. Where are we? Okay, so I already had something going on here. So we copy this. So we have got 1, 2, 3, 3 times. 1, 2, 3. 1750. 1750. 1500. 1500. 1250. 1250. When you do that, those are the caves we have. Of course, we can still add a bit of things. For example, we can add the X labels after we make the plots. POT dot X label. So that one we want we want lambda in view parameters scene. Okay, there it is. Then the Y label, POT not Y label. So that is B lambda T times 10 to the power -5. Then what comes after that? Math RM watt per meter squared, then c dot mu meter. Okay. What? This bit doesn't work. So what do I do? The times doesn't work. No, it doesn't. If I just do this, what happens? Okay. I think that seems to. Okay, just put an X. Put an X. Okay. Okay. All right. So that's what we have. So our thing works. The one we just got the one we created last time. Then we decided to use so that that's the same function which we created last time is the same function which we are kind of trying to use today. Are we clear? Is it clear? Hello? Are we clear on what we have done? That our function can actually produce these black body things. Okay. So next, in the thing says the maximum of this thing. Maximum of the above expression is given by again lambda the max t is equals to 2.898 millimeters c dot lambda given by that. The total emissive power of a black body is given by 10 10 W power T, which is the total power int 0 lambda infinity ft. I think this infinity, I'll find out very soon. If it doesn't work out, then b lambda lambda t d c. Let me search for something first. Infinity in LaTeX. INFTY. Okay, so that's the thing, and that turns out to be equals to int 0 to infinity FTY infinity defrag a lambda to the power 5 then left right e to the power b divided by lambda t minus 1 d lambda which turns out to be sigma t to the power 4 that. So that's what you have from the notes. Say all the power which is contained in the black body is given by that expression. Is it true or not? We can find out. Does it match up? We can find out if it matches up or not. Where sigma is equals to 5.67 times times 10 to the power minus 8. 1000 m this bit watts c dot m to the power minus 2 c dot k to the power minus 4. That. So in this particular case, you can also create a function which works out the total power. What we have created is a function which starts with in the function which the one which we in the one we have here, this bit, the function you have created, the spectral flux density, this only takes the temperature, and based on the temperature you work out what your stuff is. Okay, are we clear? This one, it just takes the temperature. In the other cases, for example, this equation which we have here, where we're saying total power as a function of temperature is just equals to this. So we can create a quick function so that you can have an idea of how much total power you have. Create total emissive power for function. So we're going to say define total emissive power. This one will take temperature only, so we can say calculates the total emissive power of black body at temperature temp in kelvins. So this particular case, our sigma, create variable sigma. So your sigma, as you can see from there, is 5.6 7 e to the power minus how was I writing this? Yeah, e minus, okay, just e minus 8 so here we're saying in watts times meters to the power minus 2 times temperature to the power minus 4. So those are the units of the sigma. So if you want to get what the total power is, we'll say return sigma times temp to the power 4. temp to the power 4. So return total power. Okay, so if you want the total power at 200, you just use this expression. Calculate the total black body with the power at T is equals to 2000 kelvins. In that particular case, you're just going to say total emissive power temp is 2000. That's how much power we have. Are we clear? Are we clear? Hello?
Yes, sir, we're clear.
Yeah, so this tiny function you have created, it gives us the total power at a particular temperature. So what we're trying to do here is we are trying to find when you use this black body, this spectral flux density thing, okay, when you include the when you specify from 0 up to what particular thing, up to what particular wavelength. This one here is starting at 0. Our function is not starting at 0, it's starting at 50. So we can probably even reduce it to say, okay, fine, you start at 5. We'll not lose a lot. Okay? So what we are trying to do, we are trying to work out the fraction. So we know that this thing works. So the total power at 2000 is that much. The total power at, so finding the total power is the easy part. But we also know we have that thing which is giving us the wavelength and also the range of wavelengths which we are looking at, and also what the emissive powers are. So we can modify the function which we have in a clever way, as we are going to try to do. So then the next one is that if we're trying to see how much power is there at 1750. You don't have to do this. Me, I'm just trying to show, say, okay, 1750. This is how much you have. So there's a reduction in power, as you can see. When you're at 2000, you have more power there. That's 900 something. When you come to that part, you end up with 530 something. When you're at 1500. That's how much power you have. So the power is reducing. How much total power a black body can emit, as you can see, depends on temperature. Then here, let's go. So add 1250. There. Okay. So we go to the next part. Now the next part, which what it's trying to show is, we know the bottom part of the equation, we know how to work it out. The bottom part of the equation is what we have worked out using these, the total power. The top part of the equation, we were just giving temperature, but we can specify the range of the wavelength with which we want to do things. Okay, so the fraction of energy emitted below a given wavelength is begin question. F underscore lambda t, which is a fraction. This F thing we're doing here, that's a fraction. It's going to be equals to defrag so inside the first one, this we're saying integral from 0 to infinity integral from 0 to infinity b lambda b lambda t delta t d lambda. Then the other bit integral, sorry, no, it's to lambda, not infinity here. To lambda then we get the whole thing again all the way up to infinity. Run that. This is what we have. Of course, the bottom part, this we already know. That's what we worked out here. Here, the bottom part. This is sigma t to the power 4. So this bottom integral here, from 0 to infinity, b lambda t d lambda, this just this bit to the power 4. So we get, so when you do that, again, defrag 1, sorry, 1 over sigma, then t sigma t to the power 4 power 4. So when I do that, then multiplied by this bit here. That bit there. So we have these. So here it's just a matter of solving this. Okay? Here it's just a matter of working out this, but we know what this is. This bit, we know, to be very specific, that's what we have here. This whole thing here. Are we clear? The B stuff. So we end up having the following. Copy. Which bit system? Okay. Default A. Okay, so that's what you have here. There is a substitution which is being made. They are saying in the notes, in order that we do not have to evaluate the above expression for each and every temperature, in order that we do not have to evaluate the above expression for each and every temperature, we substitute lambda t equals to x and obtain the following. So now the following thing which they obtain, that is what's going to be the basis for our computation. So in order that we do not have to evaluate the above expression for each and every temperature. We substitute lambda t for x. Where there's lambda t, you put x, and we obtain the following. So you obtain so you have f of x, the fraction as a function of x is equals to where you have substituted for lambda t so the whole thing becomes integral from 0 to infinity, then defrag so we have sigma multiplied by x to the power 5 then left b minus x minus 1. So we have these. Oh, there's a small bit left. Dx. So now what this thing which you have here, this is just a function where you've got a divided by sigma x to the power 5, then b e to the power b minus x, b to the power divided by x minus 1. This whole thing here, the thing in between the integral, this is just a function. Actually, it doesn't go to infinity, it goes up to x only. It goes up to there. It's a form of b, in my opinion, but in terms of x. Are we clear? Where we can, I think we can do this. It's a form of b in terms of x. I don't know if it's correct to do that, but where you can write what we have here as a form of bx. Sorry. Like this. This bit here is the one which is being represented by the bx. Now the good thing here is, if we can write this thing like that, so that we end up having the following bits. That where your bx where your bx is is this, then things are easy, because the only thing we need to do is we just need to integrate. We need to create a lambda for the b in terms of x. So here we create a lambda for b. This is our b in terms of x. Then we work out this thing, whatever this thing is. We work it out for those values of x. Then we're done. If you look at your labs, okay? If you look at your labs, you notice on the back page where there's a table. If I can do that, I sent something to your WhatsApp group. Were people able to download the thing? If you look at that table, where the function f of x, the table which gives you the function of f of x. Have you seen that table? Hello?
Me, I haven't opened it yet.
Why haven't you opened it yet? There's a reason why I sent something earlier when I knew that there was a lab this afternoon.
Yeah, I was having classes now.
Let me download it.
It's good that on 30th we were opening so that continue the physical one.
That's not the point, whether we are opening or not. The point is, when something is sent, at least you just have to look at it. Even if you don't understand, you look at it, or there's something which has been sent, you look at it, then if you don't understand, you show up for class.
Yes, like we downloaded, but I never had, like myself, I never had the idea.
Yeah, it's okay. Let's see. Just a minute. There's something I want to do. So I need to, I hope you people still have access to your Moodle for the course. Where is our thing? Not desktop. Just a minute. What I want to show here is that when we reach that particular stage, when you have a function like this, then we have to integrate. Then things are going to be much easier. Life is going to be... Just a minute. I'm trying to open something, then I put it on Moodle, then I open it from Moodle. I'll share the Moodle page. Yeah, first. So I've switched to Moodle. Hope you can see.
Yes, we can.
Okay. Where is that? Okay, here. Why is it doing this? How do I? Okay. file. So okay. Okay, so our thing has been uploaded. So I'll open it. All right. And I'll share this one. So that's what we've done. So basically, we are here. This bit, this particular function. Now, what you notice with your lab is they want you to reproduce this table. There is a table at the back here on your lab, which they want you to reproduce. Probably I need to send a better picture of what the values are, but that's what I managed to get with the phone. So you notice they are here. These are x values. These are the values of x, and that's a corresponding value of the fraction. How much of the fraction at that particular x value, x being wavelength multiplied by temperature. That's what x is. Okay, lambda multiplied by temperature. So each value of wavelength is being multiplied by the temperature for you to get x. So these are the values of x here. They start from this side. They start at 1,000 and 1,100 all the way up to 50,000, and they are in steps of 100. So in a case like this, we can easily generate these values. Okay, we generate these values, then we can put them in our function b of x. We see what this curve looks like, then we can work out what the area is. Are we clear?
Yes, sir.
For a particular value of x. Now I don't know. Let's see what we can do, whether it's going to work. Yeah, because what the other thing is sometimes is, oh, we'll do this or do this, but is it going to work or not? Okay, so if I share this, so create an array. Did we import numpy beginning? No, we just imported it in the function. Okay, so I'm going to do the following. Import numpy module as np. Okay, so we want to create x. So x is going to be np dot arrange from 1 these bits all the way up to 50,000 in steps of 100. So you print your x value, create numpy array x. So those are x values which you're going to use. Create numpy array x. From 1 that to 50,000 in steps of 100. Mu meter c dot k. Okay, so that's what you have here. If you print this bit, print array, so you'll say print x. So those are the values which you have for x. I think there's even one is missing, so we need to go a bit further. We do that. So with 1100, 1200, 1300, all the way up to that. So with these values of x, we are going to put these values of x in p of x. I'm trying to think. So we have our x values. We put our x values in. If we put our x values in this guy, what do we get? So let's try to create a function b. This bit here. Spectral flux. We write a new form of this function, spectral flux density. We rewrite it. Now it will not accept temperature, but it will accept x values. Okay. So it won't be accepting temperature, but it will be accepting x values. So what do we have? Let's see. So we've got an A, then we've got a sigma. So A sigma. So we have instead of B, we have a sigma. The sigma value is so I'm going to say define function, okay, create function, create function, px spectral flux density, flux density. Let's see, before we call it a day, let's try this bit. We see how what it gives us, so that we can figure out how to make adjustments based on based on these bits. This one. based on that. So we have A, the A is there. There is also B. I don't know. Then why did I remove it? There's a B value. So there's B. So B should remain. There's B. There is sigma. We need the sigma here. So sigma is going to be 5.67 e to the power minus 8 in watts times in watts times meters to the power minus 2 times k to the power minus 4. That. So we have got A, B, sigma, and x. So that's what we're getting. So we have numpy inside for the x values, because these x are going to be a numpy thing. Then we also want to use the numpy version of this whole thing. So I don't think I need this. We already have x. I think we need this. What else are we going to need? We will not need this. But we have the numerator is A. The denominator starts with sigma times x to the power 5. So the denominator starts with sigma times x to the power 5, then the exponential b divided by x minus 1, like this. That's what our denominator is. Then after that, what you're going to get is, I'm not sure exactly what kind of thing I'm going to be getting, but anyway, let me leave it. Let's see what we're going to call it something, because we're only getting one thing. We'll see what it looks like, then we have an idea of what it is. This bit. So I'll say spectral, flux density, then x. What do you get? There. Now what does this look like? I'll call this F. Let me see what it looks like. Let me try to make a plot. POT. I'm not sure what it is I'm having. And yeah. POT the plot. X spectral x POT dot show. No, what we have doesn't make sense. So what is it you have? The y values. P minus x. Okay, let's see. From SciPy. Red. Import. So what do you have? Since we have got the function, and what else do we need? So help, themes, so we need y values for the function. Okay, but this is just going to give me a number. That's a problem. Okay, let me try. There's no point giving up so easily. So y spectral x. Seems yx. Yeah, that's a problem. We're just getting a number. Whole number. So if I say for kn for k and x, seems seems odd. It doesn't make sense. seems so. Now from sidebar. Let's see. Quad. Quad. Let's see, is it going to work? I doubt if it's going to work. But no. Just a minute. Hold on. Quad. No, almost. Just a bit. Spectral. I'll call this one. I'm saying if it opened. What have I produced? Just a minute. Okay. I have something, but it doesn't seem to make sense. And it doesn't match. Does it match with what you have? Let me see. Zero. Now, guys, let's stop here. We'll continue next week trying to figure out this. Okay.